Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Wow, I have to admit, this was an absolutely brilliant presentation. I don't know if this can match the beauty of your presentation, but that was just amazing. So I'm going to describe briefly some of the recent work we've been doing on the process of rehabilitation of stroke patients. And so this is a recent project that we've been doing for the last 6 months. And more recently, I've been working on the annotation, archival, and visualization of all the data we've been collecting in this project. For us, so I'm part of a program called the Arts, Media, and Engineering program, and the focus of this program is to engage in the building of large multisensory systems with the help of multiple disciplines. So this particular project has people from bioengineering, music, visual arts, as well as a physical therapist, in addition to people like me who are from computer science. So why are we doing this? Our motivation comes from the fact that in the United States, every 45 seconds, somebody suffers a stroke. Typically, this results in functional deficits that prevent people from doing very simple functional tasks, such as, for example, reaching for a cup. So the other important issue, which is also a financial issue, is that most insurance companies are very reluctant in the United States to pay for more than 2 visits. So once you have a stroke, they're very reluctant to enable you to carry on therapy with a physical therapist to enable you to regain control of your limbs. So what is the thesis? Why do we assume that people would regain control of their limbs after suffering a stroke? So the fundamental idea is the neuroplasticity of the brain, is that if you can engage this person in this same functional task repeatedly, this person, parts of the brain will create pathways to engage, to enable this person to repeat that functional task. So the part of the brain that used to be controlling, enabling you to control your body to, for example, reach for this wire, is no longer active, but another part of the brain takes over the job through therapy. So our goal was to design a multimodal environment that enables people to engage in this therapeutic process. And the reason for that is traditional physical therapy is extremely boring. You ask the patient to, for example, reach for a ball or play around with some physical object hundreds of times. So it's extremely uninteresting to them, and they rapidly lose interest. Even though they're highly motivated to improve, they rapidly lose interest because the entire environment is uninteresting. The second goal for us was, of course, that, okay, if you're going to create a multisensory system, we must be able to archive, annotate, and retrieve this data so that the therapist and other members of the team can have insight into what is going on. And you have to remember, therapy can range from anywhere between 1 year to as long as 10 years. So it's extremely important for us to record this data for a long period of time. The other motivation is that today, physical therapists do not have access to quantitative data to understand the progress of the patient. So they take these samples, rough samples maybe every time they come to therapy about range of motion and so on. But they really do not have fine-grained analysis of something as simple as, okay, Mary came to the clinic today. How did she do compared to last Tuesday? So it is impossible for them in their subjective judgment to figure out whether it was a 1% improvement or 2% improvement or what the trend is. What is going to happen in 6 months? So we want to be able to predict this. And the only way to be able to do that is to be able to collect data over the course of the lifetime of the patient. I mean, not the lifetime of the patient, as long as this patient is engaging in therapy. Like I said, this could be as long as 10 years. So briefly, in order to contextualize the archival annotation system, I need to first explain what the biofeedback system is. And I'm just going to give a very brief overview. And this is going to appear in ACM Multimedia 2006. So the biofeedback system, the goal is to construct a system which situates the participants in a multisensory environment, in an aesthetically engaging environment where there is real-time analysis of action, of the patient engaging in a functional task, which is coupled in real time to audiovisual feedback. Now, this is a very simple diagram of our subsystem. So it has 5 parts. There is a motion capture system, which is a 6-camera Vicon system that captures the subject using infrared markers, infrared cameras, and there are markers on the subject, and this happens at a very high data rate of 100 frames per second. There's a motion analysis engine that analyzes different motion analysis parameters that sends this analyzed data to the feedback to the 2 feedback engines as well as to our database. Now, all 5 systems are synchronized to a universal timestamp. Now, the interesting thing here is that when we are talking about real time, we're talking about giving feedback at 60 frames per second. To be able to do that, and the reason we are doing this at 60 frames per second, not 100 frames per second, which is the capture rate, is because of the limitation of our monitor. It simply can't display at that large TV screen that we have could not display at a rate greater than 60 hertz. So, okay. Now, so this is a simple overview of the kind of marker setup that we have on our subject. So we have 14 markers, and they are arranged, in the manner that is shown here. And the main reason for their arrangement, there are 2 reasons for their arrangement. First is they have to be consistent with the therapeutic task. So we want to be able to determine several parameters from the point of view of the therapist, and the location of the markers are such that we can compute those motion analysis parameters. The second reason for the markers to appear the way they do is to do real-time analysis. So if you have something like, for example, markers patient, to compute all parameters needed in one which is the trade between not too many markers is too much, but not too few because it's accurate. Okay. Now, we wanted to couple action to feedback. Now, the key point for us, for my colleagues who work in visual art as well as in music, was the idea of engagement. It is clearly attractive, must be intuitive, must be little information to understand what in the function is easy to use. So the functional task that we decided to work on is something really simple. It is the ability of a person to reach out and grab for a cup. The amazing thing is that when we first settled on the function, the rest of us who have been involved in clinical trials, why is this such a difficult thing to do? The remarkable thing is that those of us who are able-bodied take for granted what actually is fairly complex coordination of different joints and our ability to form a plan to reach out and touch something. So we decided to do this because it seemed like all the things we thought of this was the simplest thing we could start with. B, challenging it from engineering the review just actually like. So we decided that there were 3 semantic images had to be present in both visuals and audio. And they had to be organized in this manner, and they had to be synchronized in time. So the 3 messages that we have was the idea of reaching. That is, so the 3 messages. One is the idea of flow, one is the idea of openness, and one is the idea of reaching. So the idea was the semantics are as follows. So when you reach out for a cup, you need to open your arm. So the audiovisual feedback needs to communicate that idea. The second idea is that as you get closer to the target, you must be instructed to grasp the target. So the semantic message should be supinate, or pronate, your hand such that you can reach out for the cup. Because after all, when we reach out for a cup, we don't reach out for a cup this way. We open our arms and we supinate. And the other very important thing is something that appears fairly trivial, is that we need to open our arms. You might wonder, why is this such an important thing? Because if you actually work with patients who've had stroke, you will find that some of them will try to reach for a cup this way. They will not open their arms at all. So it is very important for us to communicate these messages, and they have to be at the level of meaning, and they have to be synchronized. Audio and visuals have to be synchronized. So we decided to have 5 steps to this. So every subject who came in, so the first set of experiments that is described in this paper deal with only normal subjects because we want to test the experiment. And the last 2 weeks we've started our clinical trials, and I'll discuss that in the next part of this presentation. So we wanted to have 5 steps. We wanted to start with subjects who reach out for a cup 10 times. Then we wanted to produce an introductory environment that gives them the idea of what the functional task is, which is the environment that you see on the top, which is a 3-dimensional environment that obviously reacts in real time, which is at 60 hertz. And it begins to give them an idea that you're supposed to reach for a cup. The next 2 environments became much more abstract. And this is where the influence from the arts is very interesting. So my colleagues, the first thesis is that you don't need to have literal representations of a task in order for people to actually perform that task. So if you look at the top representation, which is traditional VR-based therapy, you might imagine that is the best way to represent an environment in order for a person to actually perform well. So the thesis from the arts is that for the last 300 years, for the last 150 years, we've gone on from literal representations of meaning to far more abstract impressionist representations of meaning. And people seem to parse that very well. And you don't need to have literal representations of a particular environment in order to actually be able to succeed in that task. Right? So this was also a thesis that we wanted to test out. So we created 2 abstract environments. One that the difference between the 2 environments differs in the kinds of sounds that are used. Both visual environments are similar, but the sounds that are used in the 2 environments get progressively more complex. There are richer mappings in the second abstract environment. And finally, we return to the physical situation where we test what's going on. Has there been any difference? Okay. Now, I think I probably I should skip over this. I'm taking too much time. But the key idea here is that in audio feedback, we mapped the hand trajectory velocity in the z direction to event density. We mapped joint synchrony and harmonic progression, and we mapped the shoulder to woodwind sounds, flute, clarinet, bassoon that were randomly picked. The instrument is randomly picked. The elbow was mapped to string sounds. The shoulder and elbow extensions were mapped to MIDI velocity, duration of the event, and the probability of octave doubling. So this was all done by my musician colleagues, and this is a Max MSP patch that actually did this. So that's a visual programming environment.
Excuse me.
Yeah.
Are you saying that the music responds to the motion, or the music plays the desired motion?
No, the music responds to the activity in real time.
So what the patient's doing, not
what
what
the
you want
patient's
them to do.
Well, it's a mixture of both, right? You want the sound to provide immediate feedback, but yet you want enough semantic cues to cue in. See, so this is something maybe I should have mentioned. The design of the environment is such that audio and visuals give complementary cues. So the visuals give spatial cues, tells you very, very quickly where your hand is in the visual environment. Your auditory cue gives you a sense of time. So what the auditory cue establishes is a sense of rhythm and a sense of the idea that you're doing well as far as opening is concerned. Now the reason why this works is because these guys use traditional theories of Western classical music of progression. It produces a sense of anticipation. So your brain creates this construct, auditory construct, that creates a sense of anticipation of what is the next event that is going to happen in time.
So what do you play? If I do the wrong thing and I lean forward and don't extend my arm.
So what will happen? So that's a good point. What happens is that what happens when you make a mistake, like raise, for example, if I do this, right? So immediately, if I do this, the sound will become very brassy, and you will get immediate feedback that your shoulder is in the wrong position. If you lean forward while you're doing this, it is again brassy, but with a very different timbre. So you again know that you're making a mistake. And the richness of the sound and the progressions that are there in the sound all get destroyed immediately. And all of this, this has to happen instantaneously and in real time. And the reason I emphasize this is that again, when the team, got together with, with all of us with different backgrounds, we were having this debate saying, why real time? Who cares? I mean, what's the difference between a 30 millisecond asynchrony between audio and visuals? Who really cares? But it turns out, when you're observing this, it seems like the subjective experience is wrong. That the person, when the person says, it's not really right. I can feel that there's an assynchrony between vision and sound, or I can feel that the sound is a little behind, or the vision is written a little behind. It seemed like an artifact. So when we actually, what we decided to do, all of us decided to participate in the testing of this. And it was true that we could very quickly determine asynchrony. And if there was a little bit of asynchrony, it threw us off completely, asynchrony between visuals and sound. So it became imperative that we take out as far as possible, all the systemic delays. And we tried really hard. And now I think there is still a little bit of asynchrony between audio and visuals, but it's something like 20 milliseconds. We have tried extremely hard to reduce this delay. Now, the abstract environment here, what it does is that it tries to replicate this idea of pointillistic sound construction that happens in music with the idea of all these points that are floating around. What happens is that the reason behind this representation, visual representation, is as follows. You want to give a frame right in the beginning, which cues the subject that all the particles will coalesce together and construct the picture, right? But you don't really have a sense of what the picture is. You have a fairly distorted sense. Now, as the hand moves forward, depending upon what exactly you do, several things can happen. So this is an example of error in supination. So what the subject has done, instead of opening your hand like this, this is pronation and this is supination. So as I'm not being a bioengineer, I call everything supination. So I supinate my hand, I open it like this, right? If I make a mistake, if I'm here, the visual feedback will tell me immediately that I'm in the wrong place. Okay? If my hand is in the wrong place, so there's an extensive calibration that is done to get this experiment off the ground with every person. So if I'm in the wrong location, if I'm here, for example, I immediately give feedback saying that I'm overshooting at the top. So this is an example where I'm overshooting to the right. Yeah? And on top is visual feedback that says I've overshot the target. Now you have to remember, in the three environments that we've created, there is no physical cup in front of you. Only in the physical environment, in the first environment, is there actually a cup. So what happens, I don't want to reach for that, but what happens is that let's assume that there's a cup here. In the physical environment, I would reach for it, and we would do 10 trials to figure out how well this person is doing, right? In the middle three environments, there is no cup. So the idea is that we want our audiovisual environment to reconstruct all the different sensory feedback so that I can open my arms correctly, supinate correctly, and have the right flow, which means that there should be smoothness to the trajectory. This is again very important because normal subject opening is extraordinarily smooth, but with patients, there's tremendous shaking that happens because they've lost control of their hands. So there's some validation metrics. So our results that I'm showing you here are with normal subjects. And the reasons we did this with normal subjects is twofold. First of all, there's an ethical concern. When you're working with patients, you do not want to put them in an environment which is experimental. You want to put them in an environment that has been reasonably tested out. So it was very important for us to do this ethically. So we decided to do this with 10 normal subjects to figure out, A, is our system working? B, does our environment has any impact on any performance? Because one thesis could be, the idea of reaching for a cup in a normal subject is such a learned behavior, it's not going to make any difference, right? So when we do so these are the three graphs I'm going to show you. So when we do reaching, the idea that do you supinate correctly? Turns out you can't really make out any difference in the different environments. So the kind of errors, reaching errors, these are spatial errors that you see, they're fairly similar. It doesn't seem to make any difference, right? Now, but if you look at the other graphs, if you look at openness, how well we do when we open our arms, it turns out that our environments make a tremendous difference. Now, the reason why this is important, our conjecture was when you remove the cup and introduce them to the environments, error should immediately increase because you really don't know what to do. If our environment actually works as we think it does, think it should, error should drop because you're providing the right feedback. If you're not providing the right, because remember there's no cup there. If you're not providing the right feedback, errors will continue to be high and stable. So this is exactly what we saw. Errors increase because you've gone from cup to no cup, just no sound here, right? Errors drop. When you go to the abstract environment, which has both visuals and sound, remember there is no literal representation of the environment now. Errors dramatically increase. But very importantly for us, they reduce, providing the thesis that even if you don't have a literal representation of your functional task, you can construct environments that provide enough cues to rehabilitate, right? Okay, I'm going to skip over the next slide because I want to get to archival here. So okay, maybe just 2 or 3 slides, yeah? So what are the challenges? Let me go over the main challenges here. These are all things that we've done recently, so I just want to point that out because I won't be able to explain all of this. So there are 3 challenges. First is that the data streams are occurring in real time at 1/100th of a second. There are lots of different subsystems that are spewing out data. Motion analysis, raw motion capture, audio feedback, visual feedback. We want to do video capture the room itself. We want to capture data, speech data of all the people who are talking, right? We wanted an archival subsystem that works across domains. And the reason why this is important is that when you have a team of people working from 5 different domains, each one sees the thing differently. You want to be able to archive and annotate each one's perspective, and this was hard. So we wanted to create a real-time collaborative annotation framework, a visual annotation tool that addresses that, an offline visual information framework. So let me just go over the tools, and maybe I'll just give a system diagram and our systemic approach. So the overall data rate is high, but not terribly high. It's about 1.9 megabit per second. But the reason why this is a little challenging is that it's coming from lots of different sources. We need to be able to time synchronize them, and we need to be able to store them in real time, right? So that is a bit of a challenge. We decided to go for multicast, even though it might create, the idea is that this creates, this minimizes latency. There could be synchronization issues when we record data, but we do a pre-synchronization process to eliminate that. But almost everything in our system, even though this is such a small subnet, is multicast. And the idea is it also allows scalability, and because motion analysis is so critical, it prevents people from recalculating the data at different nodes. So initially, our initial experiment, this motion analysis, some of this analysis was being replicated in audio feedback and visual feedback because it had to be done in real time. The problem is people had different implementations of the same algorithm, and that created subtle errors that blew up in the environment itself. So we decided to concentrate a lot of the analysis in one node and multicast, and said, okay, you guys are only responsible for what you're really supposed to do. Okay, let me get rid of all of this and just focus on one quick thing. Why is collaborative annotation difficult? Annotation is very difficult in this environment because you have to understand the context of the environment. Each trial, the reach for a cup, lasts only 5 seconds. There are a lot of things that can go quote-unquote wrong. And what do I mean by that? Every subject who comes in has different physical dimensions. They have a different life experience that makes us have to adjust every parameter of the system. You have to change sensitivity of motion analysis. You have to change sensitivity of feedback. Some people don't like the sounds, or some people may not be able to appreciate the sensitivity of the visuals. Everything works, but everything needs to be adapted per patient. You can only figure this out as the subject is actually interacting with the system. Every one of these events has to be written down, annotated, because we need to be able to understand, why did this person make this change? It is very difficult. So the cognitive load on this is extremely high because everybody is watching the patient. If something goes wrong or something needs to be changed, nobody really is interested in typing in a piece of explanatory text, why did I change what I did? So it was very important for us to address this. It had to be personalized because the annotation space is large. So we're looking at something like 75 different events that need to be annotated, and everybody has a different set of events. It had to be collaborative because everybody needs to be told what other people are doing, because that's another incentive for you to annotate. So very quickly, this is actually our annotation tool. We had a web-based annotation tool that gives you your current progression during the trial in real time. Every annotation tool, annotation client multicasts immediately whenever somebody does an annotation, so that the rest of the team immediately knows, hey, the visual feedback guy noticed something. Maybe there's something interesting for me to write here as well. So this was extremely important. And then, of course, they can write free text, and they can annotate their own particular subset of the kinds of things that they are interested in. So this was one part of it. The second part of it, okay, let me just quickly step through this. This is also, we've just finished this. The second part of it was that we had to be able to visualize and reveal this tremendous amount of data that had been actually archived. So we created a hierarchical, multi-scale, in time, representation of the data that was consistent with the actual experiment. And what we did was that we allowed people to annotate this as well. Because after all, let's say you're a therapist and you have done a tremendous amount of annotation, you want to be able to take a second look at the data across time scales and across maybe 6 months and say, you know what, I see an interesting pattern. That annotation has to be, the visualization tool has to enable annotation as well. So we have synchronized playback of both the action data, the analysis data, as well as our capture. So this is our actual video capture. This is the actual playback. This is what the patient sees, and this is synchronized with sound. And so right now in this, we play back the sounds and visuals of what the patient sees. The lower stream, these two are time synchronized with this red bar that moves across. It tells you what actually the patient did. So let me just conclude here, because I think I can just go on. So to summarize, we have a multimodal biofeedback system where, okay, maybe I should just leave this here. Where we have a large-scale project that deals with biofeedback rehabilitation. This is, for us, a long-term project. We plan to be working with Mayo Clinic for the next 5 years on this. There are challenges that deal with real-time audiovisual feedback. There are challenges that deal with adaptation. And there are significant challenges in archival, visualization, and annotation. Some of the issues for annotation and archival deal with representation of events, analysis, event detection. We want to be able to have a much better annotation tool that further reduces the cognitive load. We want to have SenseCam integration, because right now what we did, so this is what we captured in the last 2 weeks, was that we captured all these images, and what we want to do, and based on what Virginia said today, I think it will be really important for us to have this playback in real time, particularly for the therapist, so that, because this was now attached to the therapist. So we wanted to be able to capture what she sees and what she does. So that, and hopefully, it might be interesting to see what kind of an effect that the addition of this stream has on her recollection of the events that she participated in. Okay, I'll just stop there. Thank you.
Okay, I got to make a decision now because we're a little bit behind time. How about actually, we'll take a couple of questions for Hari, and then Dan put you off until after the coffee break, and we'll shorten the coffee break a little bit. So please, a couple of questions for Hari, and we'll go.
In the model that you're building around the events, have you applied machine learning or anything like that to understand the dynamics of it, and then maybe extend that to other patients, so there might be classes of patients that
Sure. Again, I have to mention that this was a lot of the stuff on the annotation archive was done only the last few weeks. So the biofeedback system is up. It's been complete, but the annotation archive was done only the last few weeks. I mean, the kinds of things that you saw. Yes, so that is our goal. What we are planning to do is to have a Bayesian belief network representation of the events. And our goal is twofold. A, when you have a patient, you want to be able to anticipate events based upon what you're seeing right now. So if you're seeing a patient, perhaps make a mistake, you want to cue the therapist saying, based on analysis of this patient, other patients in the same class, we anticipate X will happen 5 trials down the line. Be on the lookout for that, because that could be because she would have annotated that event to be important. So yes, exactly. We're planning to do that exactly. Okay.
Let's try and thanks again, Hari.